This is the General Circulation Patterns module. I'm Ed Zoke. Dan Bykos and I prepared this module. In this module, we will focus on using imagery to identify and monitor basic circulation features, primarily using the three water vapor channels that will be on GOES-R, since water vapor can be used as a passive tracer to follow motions in the atmosphere. Our first focus will be on an upper-level ridge using this short loop with an image every 10 minutes. Note that we have used the 4-panel format that is available on AWIPS 2. We are using imagery over the Pacific from the Himawari satellite as a proxy for GOES-R, with 3 similar water vapor bands and visible imagery. In the next slides, we will highlight some features that we can identify on the water vapor imagery. We will annotate on the loop since it is a short loop, and the features identified do not change that much over the course of a few hours. First, let's look at some details of the upper-level ridge. In each of the water vapor panels, we have drawn a yellow line. This line marks the poleward extent of the ridge, as seen in each water vapor channel. How did we determine where to draw this line? We know that flow goes around an upper-level ridge in a clockwise or anticyclonic direction, while flow around a trough is counterclockwise or cyclonic. The line marks the approximate location of the most poleward extent of the clockwise flow, and so the northern extent of the ridge. If we look at the ridge extent in each image, we can note a slight expansion of the ridge as we get lower into the atmosphere. The 3 channels of water vapor imagery allow us to get more of an idea of the 3-dimensionality of features. In this case, a dome of warmer air that gets larger in area as we go lower in the atmosphere. We can also use the flow-following features of the water vapor imagery to determine where the center of the high or clockwise circulation is located. We don't show a high center in the low-level loop because it is so dry that for this color table, there's a broad area with only one color, making it hard to track the flow. One might try different color tables to get the most out of the water vapor channels. The overall dry signal seen in the ridge is consistent with a broadly subsiding, warming, and drying air mass. Monitoring the change and extent of this drying are useful for determining the strength of the upper-level ridge. Note here that even in this short loop, we are seeing an increase in the drying, warm, or brightness temperatures, and by inference subsidence in the mid-level water vapor image. Even though the atmosphere is quite dry, we see from the visible imagery that the very low levels over the ocean are moist enough to sustain at least shallow convection. Although we would not expect this convection to develop much given the strong subsidence inversion associated with the ridge, the fact that we see it emphasizes the point that while GOES-R will have a new low-level water vapor band, seeing a very dry signal in this band does not necessarily mean that the dry air extends all the way to the surface. Substantial upper-level flow often extends around the edge of an upper-level ridge, as is the case here. How can we use the water vapor imagery to diagnose the jet stream? In the mid and high-level water vapor images, we have indicated the approximate location of the core of the polar jet stream shown by the white contours. In these channels, we will typically see an elongated zone of warmer brightness temperatures corresponding to drier air on the cyclonically sheared side of the jet axis, in contrast to an increase in moisture, or even a solid band of clouds, if enough moisture is present, on the anticyclonically sheared side of the jet. We can think of why this is so by remembering that the polar jet is associated with the thermal contrast, or baroclinicity, across a frontal zone, with warmer and more moist air to the south. In our case, there are not many clouds, and all we see is the elongated dry zone that helps us identify where the polar jet lies. The dashed white contour in the high-level image depicts what appears to be a jet streak embedded within the polar jet, determined from the fast-moving patches of cirrus in the imagery. At the far western edge of the images, there is also a subtropical jet, which is typically located relative to cloud and water vapor imagery in a similar way to the polar jet. We have marked the approximate location of the subtropical jet with a yellow contour on the high-level water vapor image, where it is best seen. In this case, we do not see much of a dry band signal, probably owing to a branch of the polar jet lying so close by. Now let's take a closer look at the jet stream zone around the periphery of the upper level ridge. In our case, a broad upper-level trough is found to the north across the North Pacific. Within the jet stream, we find transient, shorter wavelength troughs, known as shortwaves, and we have marked their position by white arrows at the beginning of the loop. We can think of each of these shortwaves as a smaller scale version of an overall trough, with sinking air in the dry conveyor belt behind the axis of the shortwave and rising air in the warm conveyor belt ahead of it. Since the amount of moisture will vary, we may not see much of a signal in visible or IR imagery. But shortwaves can be revealed more easily in water vapor imagery by a couplet of drier and warmer brightness temperatures in sinking air behind the wave and an area of more moist air and colder brightness temperatures in the rising air ahead of the center of the shortwave. Notice how the different shortwaves appear in the various water vapor bands, some more apparent at different levels in the atmosphere. The two most well-developed waves at the eastern edge of the imagery are associated with a pair of cyclones seen in the visible imagery. We will discuss some of the structures seen with shortwaves in the various water vapor channels in more detail with the next case. In our next case, we look in more detail at upper-level troughs. The loop shown here covers a very active period, with the jet stream farther south into the Pacific than what we saw in the last case. We have zoomed out a little and again use a loop of Himawari imagery as a proxy for GOES-R and a 4-panel display that features the 3 water vapor channels that will be on GOES-R, as well as an IR channel, similar to what we now have on GOES. This loop extends over a longer period, so we have chosen to look at imagery at hourly intervals. Next, we will point out some of the features in this loop with one static image, early on in the loop at 12Z on 1 May. Then we will return to the loop so you can see how these features evolved. First, as we did before, we show the approximate poleward extent of the upper-level ridge by the yellow line, this time overlaid on the high-level water vapor image. Since we often overlay different height analyses with satellite imagery, on the mid-level water vapor image, we show the approximate location of the 570 decameter height line from a 500 millibar analysis. Across our domain, we see 2 long-wave troughs, one on the left side over Asia and the other in the Central Pacific. The different shape to the 2 lines reminds us that water vapor imagery shows 3D flow through different levels of the atmosphere. Since the yellow line was drawn following the flow, we would not expect it to always resemble the white line that is taken from an analysis at a single level. Also shown are the 2 centers of the upper-level lows and the upper-level high, located by looping the water vapor imagery to find the circulation centers. There are 2 distinctly different upper-level lows. The one in the far eastern edge of the domain is seen in all 3 water vapor images, but the main moisture signal is at high levels. And in the IR image, there is little reflection of this feature in the cloud field. When we return to the loop, you will notice that this system gradually weakens with time. Contrast this with the closed upper-level low farther north. We can tell that this is a mature and deep system by the rings of moisture wound around the center in the various water vapor channels. This upper-level low had a central height of 516 decameters at this time and was separated from the main flow. The low is gradually weakening over the time of the loop, as will be seen in the water vapor imagery by the gradients gradually going away and the moisture becoming separated from the center of the circulation. At the surface, there is similarly wound-up looking cloud features in the IR image, a classic signature of an occluded storm. Now we look at a couple of the important shortwaves that are embedded within the 2 main troughs. In the western portion, 2 shortwaves are noted by the thick white arrows. The southern wave is within the subtropical jet and is tilted out of the low-level image. Although this is not a particularly strong wave, we will see in the loop that it moves to the northeast and interacts with the stronger northern shortwave. The northern shortwave has a well-defined signature of warmer brightness temperatures associated with sinking motion and drying in the dry conveyor belt on the west side of the shortwave. This signature is seen at all 3 water vapor levels, and after this time it strengthens, initially at higher levels and then quickly down through the lowest water vapor level, a signal of a deepening wave. Indeed, after this wave interacts with the southern wave, a deep cyclone develops in northeastern Asia. The second shortwave we have highlighted is marked by the thick yellow arrow in the Central Pacific, pointing to an area of warmest brightness temperatures that marks the strongest localized subsidence within the fairly broad subsident region of the overall trough. This shortwave is approaching the stall frontal zone noted earlier and evident in the IR imagery. However, as we will see in the next loop, the drying signal with this shortwave does not intensify over time, and this wave continues to progress eastward without deepening. As a result, we only see limited development along the frontal zone. Here's the loop again with images at hourly intervals. Recall the features we noted in the snapshots: the progressive shortwave just noted and the lack of development, the gradual filling of the deep closed low at the northern edge of the domain in contrast to the weakening upper level low farther south, the strengthening shortwave over the western portion of the images and how it interacts with the wave in the subtropical jet, leading to the development of a strong cyclone. And finally, notice the slowly westward moving cloud clusters across the southern Pacific. These are easterly waves moving to the west beneath the upper level ridge. There are other tools that try to put together information from various bands into a single image. The RGB air mass product is an example of such an image, using the 3 water vapor bands along with 2 IR bands. The idea is to better depict the different air masses. This loop focuses on the 2 interacting short waves that we saw in the last loop that led to the cyclone in eastern Asia. This imagery is discussed further in the cyclogenesis module. In summary, the new water vapor channels on GOES-R, along with other products, will enable one to visualize more of the atmosphere and with greater spatial and temporal resolution than we have today.